A human's attempt to understand the intelligence. Well, first a disclaimer that this presentation contains my personal opinions beside the scientific accepted facts in academia, so don't expect it to be fully accepted by the science community. Well, purpose is to understand the intelligence and build a superior intelligence than what currently we have. Well, what do we have? And also the motivation behind this talk is to raise the right questions in your minds and not to answer them, but to raise the questions. We want to build a superior intelligence. Why should you care even? Well, have you asked yourself, what are you doing in this strange universe? There are 100 billion galaxies in the world and we are just like a dust wandering around. Why are we here? Have you asked that? Well, I asked it many times, and if you have asked yourself this question, I think you need to care, because building a superior intelligence would help us to answer these questions. Well, I think universe had the same question too, and it came up with a plan. It started first with combining all different kinds of molecules of carbon to come up with a complicated structure which we call it protein. And then an interesting properties of proteins appeared, which was self-replication. These molecules were able to self-replicate themselves. Then we called it life. But universe didn't stop here. It continued playing with these codes, which we call them DNAs, with a very brutal way by eliminating the weaks, survival of the fittest. We call it evolution. Well, universe was really lucky because randomly it came to a point that one of these species became intelligent. Well, what is intelligence? Can someone give me a definition? I want just one answer. Yeah. Ability to make models. What is a model? A very simpler definition. Can I have one definition? Self-awareness. Well, you might be self-aware but not that intelligent. Humans. Well, what discriminates humans' intelligence from other animals? How we behave. Well, how do you behave that it makes you intelligent? Okay. As you see, it is really hard to answer this question. It's really hard to say what is intelligence. Well, I have my own definitions, of course, but first I want you to see this video.
And finally from us here on the webcast today, a story that might cause some of you to question whether or not we human beings really are the smartest creatures here on planet Earth. Japanese researchers created an intelligence test that pitted humans against chimps. And in the end, we look like chumps. Here's Bill Blakemore.
First test. Can chimpanzees count from 1 to 9 in the right order in return for a peanut or other tasty reward? Yes, they can. Now, if you just flash the 9 numerals for a moment, then cover them, can a chimpanzee remember where each numeral was and still get the order they were in right? Yes, for another tasty treat. This chimp got this wrong once, but thought nothing of it and, undaunted, went right back to getting them all correct. Now, if you flash just some of the 9 numerals, then cover them, can a chimp A, remember where each was, and B, in the right order, even though some were missing? Yes. Slowing down not one bit. And note, chimps can also eat and memorize at the same time. Not only that, if right after the numerals are flashed, the chimpanzee is then distracted, say by some monkey business over to the right off camera, or perhaps by another good-looking chimpanzee, and then returns to it, no problem. Just keep the goodies coming. Now, can another primate species, the adult Homo sapien, do the same? Well, okay. And again? 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 One more try? Well, okay. But actually, chimpanzees did much better than humans in this flash and remember test, leaving the Japanese human researchers scratching their heads. One possible theory: chimpanzees care more than humans about peanuts. Bill Blakemore, ABC News.
It could be it. It could be that reason. But we will get back to this with another explanation. Well, my definition of intelligence is the capacity of imagination or simulation of the environment and being able to predict based on that. It's all about compression of the information. If you are able to compress the information around you, and if you are able to model it and predict the future, even if you are not even acting, even if you are not behaving, you might be intelligent. So, this is very tricky. What about problem-solving abilities? Well, that screen is gone, but it's okay. I'm gonna look at this. Well, there are two ways of solving intelligence, as I believe. Well, the first way is to understand the intelligence from biological way by studying the brain. And the second way is understanding what intelligence makes us able to do by the symptoms. Well, if you consider the first one, there are almost same amount of neurons in your brain to what we have, the amount of galaxies that we have in our universe. So if you ask me, I think this wouldn't be the best way to do it, because you need an AI to solve brain, then to solve AI. So I don't think that's a good answer. So I chose the second one. So if you look back at the history of solving intelligence by humanity, just look at the history, you could see that actually we were on the right track. At 1950s, humans started seriously thinking about the ways to build an artificial brain. Pitts and McCulloch started building artificial neurons, and Alan Turing proposed his intelligence test, which is not relevant anymore, based on what you already saw. And at 1950s, at Dartmouth conference, the term artificial intelligence first coined. And after that, the field was born. Well, they were quite optimistic at those times. And at 1965, Ivanchenko introduced multi-layer neural networks, which was an early version of deep learning, which we call it today. And then at 1970, Marvin Minsky told that in 3 to 8 years, we can build a human-level intelligence. Well, it didn't happen. But there was a good improvement here at 1975, and that was the last of it, which was backpropagation. Backpropagation was the core of all what we are doing with neural networks right now, to train all our models. Well, after that, there was a winter coming. And this winter lasts almost 20 years. Is it? I don't know. You can subtract it. Well, there was a savior. Where was Jon Snow? Well, did we have a Jon Snow to save us? He did. This guy saved us from the winter. His name is Sepp Hochreiter. Who knows Sepp Hochreiter? 3? Okay. This means that we don't really know about the history of AI, because this guy found out why Ivanchenko at those times were not able to train multi-layer perceptrons and get more performance by adding more layers. This guy discovered the problem with deep learning. Because if you were trying to add multiple layers in your neural network, we were not able to train them efficiently. Because if you take the error at the last layer, well, this is how it works if you know a bit of machine learning, and you need to backpropagate the error to the earlier levels, earlier layers, it vanishes to 0 or explodes to infinity. That's why we were not able to train earlier layers, and we were just training the latest ones. That's why people started solving this problem. And then deep learning hype born. Well, at 1997, Jürgen Spitzhuber, together with Seppo Kreiter, proposed LSTMs, long short-term memories, which is used currently in your smartphones to detect the speech recognition. Most of the tasks that you are saying to your Google Assistant or Siri are using LSTMs in the background. At 1998, Jan LeCun, Facebook AI director, proposed ConvNets, which are heavily used in document recognition. 2006, Jeffrey Hinton, Google's AI director, proposed an unsupervised way of training neural nets, and after that, deep Boltzmann machines. After that, the first GPU usage, 2019, NVIDIA graphic cards was used heavily to train massive parameters of neural networks. And 2014, Jan Goodfellow introduced generative adversarial networks, which I'm gonna come to this. And then DeepMind, which was acquired by Google later, built AlphaGo, which beats Go boarding game champion. And I'm gonna show you one of the works, interesting works of DeepMind about Atari games. This is really interesting to see. Well, this model is based on deep Q learning and is trained on a Pong game, and it doesn't know anything about the Pong, about the ball, nothing about it. It just sees the pixels, raw pixels that we as humans also see, and it only knows about the score, and it just tries to maximize the score. So first, it's not really playing well. First 10 minutes. And it's training on the fly by observing the score, if it can get a higher score or not. After 120 minutes, it plays like an expert human. Well, I'm not sure I can play like this. But after a while, something really interesting happens. After 240 minutes, the magic happens, and this model finds its way to efficiently get the highest score by digging a tunnel in the corner just by the minimum action required to get the highest score. And this is not for this game only. This happens for most of the games. And it really surpasses human level. But there are some games, if you know about them, like Montezuma's Revenge, that it was not able to discover, but I'm gonna come to that later maybe. Well, one of the interesting things that researchers came up recently was being able to let the neural networks dream. And what do we mean by dreaming is to producing data by the existing data. Generative adversarial networks was produced based on two different neural networks. Was one discriminator and the other one was generator. By a random noise, it was generating fake images, and the discriminator was just discriminating between the real train set or the fake one. And by training this, it becomes each time more efficient by producing fake images, which is really, really close to real ones. And each time you can produce a fake image, which is really, really close to your training set, and eventually you will have an infinite train set. Or you can dream about your data. Well, this is quite exciting, right? But there's still something missing here. So far what we had is weak AI. Why do we call it weak AI? Because it's narrow application specific. Because if you get a model that was trained on speech recognition, you cannot apply it on NLP, you cannot apply it on autonomous driving. This is really fascinating that we can do this and surpass even human level, but we cannot build something that is general purpose problem solver. And why is that? Well, let's go back to the chimp, because we don't want to lose the game, right? Against the chimp. Well, scientists proposed a hypothesis called cognitive trade-off hypothesis, which was based on this image. They think that our brain is structured in 3 different parts. The third one is the reptilian brain, which is responsible about fight or flight, aggressive drives, controlling automatic functions like blood flow, heartbeat, etc. And the second one is the mammalian brain, which is on top of that, and it is about generating emotions and attachment center, eating, reproduction, stuff like that. And the third one, which is only about primate brain, including human, it's about rational logic and thinking and more spiritual values. So they think that in chimpanzees, the part that is responsible for visual cognition is bigger than the first part, which is responsible for language. That's why they cannot really talk efficiently, but we can talk. But our visual cognitive memory is not as powerful as chimpanzees. So does this mean that they are more intelligent than us? I don't know. Well, there's another hypothesis that it says the short-term memory of chimpanzees are far better than humans. This is another hypothesis. Well, from the perspective of cognitive psychology, if you look at it, if you look at these photos, by looking at them, you immediately get the impression. You can feel every image by just looking at it. You don't need to think about it. What is it telling? This is intuitive. This is intuition. This is what we call it system 1 in cognitive psychology. But the second one, solving equations, it's about logic and reasoning, which you need to think, you need to write it down, you need to invest some time. It's slow and it requires more energy. This is system 2. That's why we call this dual process theory. System 1 is very intuitive, it's very fast, but system 1 is very fast, system 2 is very slow, and it's about diagnosing very complex tasks. So system 2 is far more powerful in humans than chimpanzees. Well, I think we are missing a link here, a powerful link that connects system 1 to system 2 in what we currently have in AI field. Well, we come to this image, which I think is really interesting. This shows basic understanding of environment, system 1, the intuition. At top of it, there is reasoning, what humans do, what we are able to do. Reasoning comes after intuition, very simple things. For example, if you touch a heat surface, you could get burned and you just take care of your hand. Another layer comes about discovering the rules of your environment, physics, science. Physics discovers the laws governing our universe, but of course it is constrained and full of assumptions. We have gravity law, we have constraints, we have limitations. But there is another layer on top of this, which is mathematics. Mathematics doesn't have that limitations. You can have a free world, you can even build another world without the limitations of what currently in physical world we have. But even we can go further than mathematics. It becomes imagination. What you have in your imagination is the true knowledge. But when you want to communicate it, you need to symbolize it. You need to narrow it down to assumptions, to symbols, and you just crush the knowledge and then communicate it. That's why we write a lot of books just to communicate one simple thing. This is the barrier in information. That's why I think we need to build a new framework which is more efficient than what currently we have, because I think mathematics, the symbols defined in mathematics, can be biased with the history of all mathematicians we have, because they had all their own subjective experience. What else are we missing? Well, I think we didn't touch consciousness, we didn't touch computation power and creativity or curiosity. Well, about the first one, consciousness, there are many, many theories, and it is as hard as defining intelligence to understand what is consciousness or being self-aware. Of course, there are definitions, but it's not satisfactory for me. But I wanted to look at this from the AGI perspective, artificial general intelligence. An intelligent being, I think, doesn't necessarily need to be self-aware. But it was a key in evolution to bring the species to this point as a motivation to understand the universe itself. It doesn't necessarily mean that that being should be self-aware to become intelligent, but it was necessary for us, for humans, to start seeking, why are we here? What am I? So it is really important, but if you want to build a superior intelligence, it is not needed. What about computation power? We use a lot of CPUs and GPUs these days to train our models. And despite of this fact, our brain uses just only 13 watts and does all the complicated tasks. Well, this is really miserable, right? We can't do much with silicon. Or do we really need to stick to silicon? Because, well, biological organisms can do it with much better power, maybe. I don't know. What about curiosity and creativity? Let's watch this video.
There are many research projects about teaching an AI to play video games well. We have seen some amazing results from DeepMind's DeepQ learning algorithm that performed on a superhuman level on many games, but faltered on others. What really made the difference is the sparsity of rewards and the lack of longer-term planning. What this means is that the more often we see the score change on our screen, the faster we know how well we are doing and change our strategy if needed. For instance, if we make a mistake in Atari Breakout, we lose a life almost immediately. But in a strategy game, a bad decision may come back to haunt us up to an hour after committing it. So, what can we do to build an AI that can deal with these cases? So far, we have talked about extrinsic rewards that come from the environment. For instance, our score in a video game, and most existing AIs are, for all intents and purposes, extrinsic score maximizing machines. And this work is about introducing an intrinsic reward by endowing an AI with one of the most human-like attributes, curiosity. But hold on right there, how can a machine possibly become curious? Well, curiosity is defined by whatever mathematical definition we attach to it. In this work, curiosity is defined as the AI's ability to predict the results of its own actions. This is big, because it gives the AI tools to preemptively start learning skills that don't seem useful now, but might be useful in the future. In short, this AI is driven to explore, even if it hasn't been told how well it is doing. It will naturally start exploring levels in Super Mario, even without seeing the score. And now comes the great part. This curiosity really teaches the AI to learn new skills, and when we drop it into a new, previously unseen level, it will perform much better than a non-curious one. When playing Doom, the legendary first-person shooter game, it will also start exploring the level and is able to rapidly solve hard exploration tasks.
Well, this is interesting, right? Humans are curious too. Well, what should we do now? Well, I think, as a conclusion, we are missing a powerful link between intuition and reasoning. We don't necessarily need to build a conscious being, and we don't necessarily need to build it on silicon. We don't necessarily need to copy the brain. Maybe it's not the best design. Well, evolution brought us to this point, but it doesn't necessarily mean that this is the most efficient intelligence that we could have. We might come up with a better one. And to end this, I'm going to say that we are the eyes of the universe to see itself. So let's be those eyes and contribute to the universe. And I'm going to end this with, of course, Jorgen Schmidhuber. And
a new type of life is going to make the universe intelligent. Now, of course, we are not going to remain the crown of creation. Of course not. But there is still beauty in seeing yourself as part of a grander process that leads the cosmos from low complexity towards higher complexity. It's a privilege to live at a time where we can witness the beginnings of that and where we can contribute something to that.
Thank you.